Thanks, Dave. Again, my name is Andrew Muñoz. You may recognize me from last year, where I talked about automatic simultaneous multiple well ties. And in computing those, I used dynamic warping. So this is just a different extension of dynamic programming to another subject that you haven't really that we haven't really done much for. Thank you. We haven't really extended dynamic warping to yet. So, okay. So in fact, the application here is to do non-hyperbolic moveout analysis with dynamic programming, and specifically using semblance spectra. Now you saw an example with Ilya that you can estimate parameters such as VNMO and eta without semblance spectra using glossy independent layer stripping. But we're going back to the semblance spectra because found a nice way to constrain a curve that you would fit through a semblance spectrum, which would give you the optimal parameters. And we'll go into a little more detail about what I mean by that. So first, the model that I used was the BP-TTI model. And with this model, we're given known parameter fields. We have vertical p-wave velocity, delta, and epsilon. So I chose there's also given to us are CMP gathers that are modeled with an elastic anisotropic finite difference code. So ideally, this should look like as close to real data as we can get, while still knowing the parameter fields so we can test this algorithm. So the white triangle you see at the top of these parameter fields indicates where I chose a CMP gather, and I chose a CMP gather there specifically because I'm trying to avoid any effects from the glaring salt body that you see in that in these parameter fields, and the reason being is we want to try to approximate a horizontal layering. So, but still have anisotropy and vertical heterogeneity. So the CMP gather that I told you about is here, and you can still see a effect from the salt, as I'm pointing out here. So this is likely a reflection from the top of the salt. So there are still going to be some reflections that don't give us good estimates, that don't give us accurate estimates of VNMO and eta, which is what we're going for. So if we use the non-hyperbolic moveout equation, we can flatten this gather with parameters estimated using our method. So we want to flatten these gathers because this is the process that's involved in creating semblance spectra, and this is a QC to tell you if you have if you're estimating your parameters correctly. So most of the primary reflections in this gather are flattened, and these are using the parameters that we estimate with our method. So we compute semblance spectra, and you'll notice that this is a two-parameter semblance spectra, and it contains one axis with VNMO and one axis with eta. And notice that I'm using effective parameters of VNMO and eta, and so you can see how in hotter areas, warmer colors on the semblance spectrum indicate higher values of semblance. And those higher values of semblance correspond to more correct values of VNMO and eta. But you notice that in on the horizontal slice, there's a trade-off between VNMO and eta, where this tends to increase with depth, and it becomes more difficult to estimate VNMO and eta with depth. And our solution will help with that. So using dynamic programming, we can solve for optimal VNMO and eta subject to constraints on how fast VNMO and eta change with time. And I'll go over in a little more detail about those constraints. And the difference between our method and other methods which might try to fit a smooth curve through the semblance spectra to hit as many semblance peaks as possible is that we are applying hard geophysical constraints through dynamic programming, whereas in other methods where you're fitting a smooth curve, you don't really know how smooth is smooth and what is the optimal smoothness for a curve in the semblance spectrum. So the resulting estimated effective parameters are compared to the model parameters, and so we compute the effective model parameters from this interval parameter fields that I showed you earlier. And for BNMO, I show the percent difference, and for effective eta, I should show the absolute difference. And we're generally below 1% for BNMO and below about 0.02 for effective eta, where our effective etas go up to about 0.15. So now I'm going to show you an example of how we do this dynamic programming approach with a simpler method, or excuse me, a simpler semblance spectra, where we use hyperbolic normal moveout to compute our semblance spectra. So, given the same CMP gather, we can flatten the CMP gather using the hyperbolic moveout equation, and as I'll show you later, this isn't as flat as it would be with a non-hyperbolic moveout equation, because in the farther offsets, eta controls the travel times a little bit more than BNMO. So using this hyperbolic moveout equation, which is primarily controlled by this BNMO, which we're trying to estimate, we can compute from the CMP gather a semblance spectra. So this is a simpler spectrum than what I showed you before, since we only have one parameter that we're estimating. So if we were to just do a really simple a really simple solution would be to pick the maximum semblance at each time. And so these peak semblances would look like this. And for the most part, in areas where we have high values of semblance, we get a good estimate if we compare it to the true values shown in the solid line here. Shown in the solid line, but of course between these semblance peaks, we don't see. There's not a very good estimate of the real BNMO, and of course we wouldn't do this we wouldn't actually do this to estimate BNMO. We'd use more advanced techniques. So to illustrate the dynamic programming approach, what I'd like to do is discretize these axes to make it more similar to what you've seen with dynamic programming. So time is going to be I, and BNMO is going to be j. And this is just a temporary transformation. So now semblance is a function of I and j. So in the dynamic programming approach, for our given semblance spectrum that we compute, then we find a sequence of sampled BNMO, which maximize the sum of the semblances for those BNMOs. And this is subject to constraints on how fast those BNMO values change with depth. And these constraints are really important, and we can relate them to geophysical parameters, and I'll show you that in a little bit. So this is really similar to dynamic warping. And in fact, it's a very easy extension from the dynamic warping code. So the semblance spectrum acts as our alignment errors that you would see in dynamic warping, and many of you saw those alignment error plots yesterday. And in order to find these NMO velocities, we maximize the semblance, whereas we minimize the alignment errors in dynamic warping. And as I'll show you a little bit later, we constrain the derivative of the NMO velocities with time, and in dynamic warping, we constrain the derivatives of the time shifts. But what's important about that is that we can relate these derivatives to geophysical functions. So given our semblance spectrum, we use the dynamic programming approach and can find a much better estimate of BNMOs than are just picking peaks at each time, which of course was a silly solution. But compared to the real solution, we have we're pretty close. But there are still some small differences. There's a bias, especially in the offset to depth, the intermediate offset to depth ratios, and this is because we're not taking into account vertical heterogeneity and anisotropy in computing our travel times with the moveout equation. So that leads me to back to the non-hyperbolic moveout. So given the same semblance spectrum, we can flatten this CMP. Given the same CMP gather, we can flatten it with our solution for NMO and eta. And if we zoom in to this set of these times, I'd like to compare it to the hyperbolic moveout. So here we have the gathers flattened with non-hyperbolic moveout, and if we go to the gathers with hyperbolic moveout, we can see that the non-hyperbolic moveout, if you go back, the non-hyperbolic moveout are flatter than the gathers flattened with the hyperbolic moveout equation. So you saw this in Ilya's presentation. Of course, he used azimuthally varying VNMO and etas. Ours is only for one azimuth, but they're still effective parameters. And so these are the parameters that we are estimating from our semblance spectra, which we compute from the CMP gather. So again, this is the two-parameter semblance spectrum. And if we just pick the peak semblance at each time again, we get an estimate of VNMO, which isn't too far off where we have peaks of semblance, but where for effective eta, it's wildly oscillating, and there's not even close. So there's definitely a difficulty in estimating eta, which many of you already know, and you can't do it just by picking maximum semblance at each time. So again, with the semblance spectrum, I want to discretize this again to demonstrate the dynamic programming approach. And again, time and VNMO are I and j, and now we have this third parameter, effective eta, which is k. So in the same way I showed you the hyperbolic assumption, given the semblance, this two-parameter semblance spectrum, we want to find optimal VNMO and optimal etas to maximize the sum of the semblance along the path of those VNMO and etas through the semblance spectrum. So again, this is subject to constraints on how fast VNMO and eta can change with time. So naturally, these parameters relate directly to the derivatives of these effective parameters. So the bounds of the constraints that dynamic warping are directly related to the derivatives of these parameters that we're estimating. So it turns out that since we have analytic expressions for the effective VNMO and effective eta, we can use bounds on the interval parameters to determine what these derivatives are, and therefore determine what the bounds on the in dynamic warping are. So this is really the key difference between our method and any other method that just kind of fits a curve through a semblance spectrum, because we're using real geophysical constraints to determine the bounds on how fast this curve can change, or how smooth this curve is. So the bounds on the interval parameters are pretty generous. The lower bound and the upper bounds on interval VNMOs, and notice this is a lowercase v to indicate interval VNMO, are quite large, and same with the interval etas. They're basically in the range of possible realistic interval etas. Of course, they can go beyond this, but this would include these bounds would be just fine for many geologic models. So if we compute the derivatives of these parameters, then we see that we get from the bounds and the interval parameters, we compute the derivatives. We get upper and lower bounds on these derivatives. And if we compare this to the derivative of the model parameters, so from that we compute from the parameter field, we can see that generally we are constraining we are constraining these derivatives with plenty of room to spare. So again, given the semblance spectra, we use a dynamic programming approach to estimate a solution using using geophysical constraints, and looking at this, looking at the differences between these and the model parameters. We can see that generally we're below 1% difference in the BNMOs and about 0.02 on absolute difference on effective ETAs. So this approach solves a lot of problems that we have with trade-offs of VNMO and effective ETA with time. And so here I'm just slicing through each 1 second at a time. So I'm essentially randomly choosing these slices. So we have VNMO versus ETA, and you notice here in the shallower depths we have large opposite to depth ratios. So the maximum semblance lines up with the estimated semblance lines up with the model semblance. So ideally we have the estimated semblance, which is a hollow circle, cover the known parameter, which is in the known parameters, which is represented by the solid circle. So as we go deeper, you notice that here we're not even intersecting a semblance peak, and this is another advantage, is that we don't have to strip out the semblance peaks from the spectrum. We just use the entire semblance spectrum, but yet we're estimating the known parameter extremely well. And as we go a little bit deeper, you start to see the trade-off between VNMO and ETA growing larger, and how the peak semblance starts to move around quite a bit, and then as we go very deep, again, I'm not completely intersecting a semblance peak here, but the trade-off between VNMO and ETA grows much larger. So ultimately, we can use this automatic method to quickly and seems fairly accurately determine VNMO and ETA, and use geophysical constraints to do so. So the next application of this, I think the next step would be and what I'm working on currently is to use the spatial to constrain the spatial variation in these parameters. So similar to you would see with dynamic image warping, and hopefully get even better results with VNMO and ETA. So the main points are that we can automatically compute VNMO and ETA from the semblance spectrum using geophysical constraints, hard constraints on the interval parameters related to these. So I would gladly take any questions, and I want to thank real quick Tariq when he visited, had a lot of good conversations, Esteban, Deshaun, and Simon for a lot of good talks, and Ilya for motivating a lot of these ideas in his class, and the BP for providing this data set. Thank you.